Hello again. We're going to continue our discussion on extreme values. Last time we left off looking at the discriminant, and now I'm going to show you how the discriminant is used to determine the various maxima and minima points on any particular 3D surface. So I'm going to hide this picture so that we can see all the necessary data and information on the following slides. So we're going to start our discussion with the second derivative test. So for functions with continuous second order partial derivatives on open disks containing a particular point, x0, y0, if f has a stationary point at x0, y0, then we know the following four items. Under certain conditions, it would have a relative maximum, a relative minimum, a saddle point, or the test would be inconclusive. You would notice that all four of those conditions are based off the value of the discriminant. If you recall, the determinant of the Hessian of f at a particular point is called the discriminant. So we'll have a relative maximum if the discriminant is greater than 0, with either the second partial with respect to x or the second partial with respect to y being less than 0. You will have a relative minimum if the discriminant is greater than 0 and the second partial with respect to x or the second partial with respect to y is greater than 0. You will get a saddle point if the discriminant is less than 0. And if it turns out the discriminant is exactly 0, then you can determine nothing using the second derivative test. So let's see if we can actually apply this. So here's a function. F of xy equals 4x squared minus 8xy plus y squared plus 3y plus 5. I want to describe the behavior of f. So when we describe the behavior of f, we should talk about any extrema that it has, and also whether or not it has global extrema, or if the function were to increase forever in either the positive or negative z direction. So we're going to need a whole lot of partial derivatives in order to figure out what the discriminant is in order to be able to apply the second derivative test. So in this case, with the polynomial function here, it's pretty easy to find these multiple derivatives. I'm going to assume that it should not be that difficult for you to find the first partials. This is the one with respect to x, this is the one with respect to y, and then finding the second partials. This is the second partial with respect to x, the second partial with respect to y, and then lastly the mixed partial, which is either taking this derivative with respect to y or this derivative with respect to x. And in both cases you get -8. So we're going to use those with the Hessian and the discriminant in a moment, but first of all we need to know where we have critical points, because it's those critical points that we're going to investigate as possible locations for extrema. So the critical points occur where the gradient is equal to the 0 vector or it's undefined. And remember that the gradient is a vector valued function where the first component is the partial derivative with respect to x and the second component is the partial derivative with respect to y. And so we're looking for where that gradient is equal to the 0 vector. So we can individually solve each component. When does 8x minus 8y equal 0, and when does -8x plus 2y plus 3 equal 0? Basically we have a system of equations. From the first piece, if 8x minus 8y equals 0, we can conclude that y must be equal to x. And then with the second piece, we can replace the expression 2y with 2x, since y is equal to x, and solve this simple linear equation to find that x equals 1/2. And then since we know that y is equal to x, y is also equal to 1/2. There are no places where this gradient is undefined. Both components are simply polynomial functions. so we have no difficulties with undefined values there. Therefore, the only critical point, which also happens to be a stationary point, is the point 1/2, 1/2. So we can plug the point 1/2, 1/2 into the discriminant. So we're going to find the determinant of the Hessian of f at the point 1/2, 1/2. So what I've done here is plug in the point 1/2, 1/2 into the second partial with respect to x, that expression, the second partial with respect to y, that expression, and then the mixed partial, and we'll square it. 8 times 2, 16, minus 64 is negative 48, which is less than 0. So we have the Hessian being less than 0. If we go back to our list of the second derivative test, let me find that really quickly. Here. There's our second derivative test. We have a case where the Hessian is the discriminant of the Hessian, or the determinant of the Hessian is less than 0. Therefore, at 1/2, 1/2, f will have a saddle point. So let's go back here, and we get 1/2, 1/2 to be a stationary point. We said that that discriminant is less than 0. So 1/2, 1/2, 23/4 is a saddle point. And I got 23/4 by plugging 1/2 in for x, 1/2 in for y, doing the arithmetic, and we find that the z coordinate is 23/4. So it's the only stationary point. It turns out to be a saddle point. We should also talk about the end behavior of this function. What happens? Does the function forever go up towards positive infinity and negative infinity? And we will see that that is in fact the case. Notice that the limit as x approaches infinity of f of x comma 0. So we're looking at the limit of this function along the certain path y equals 0. So along the path y equals 0, this term goes away, this term goes away, and this term goes away, and you're left with the function 4x squared plus 5 along that path. And when we plug in infinity for x, we get that that is going to approach positive infinity. So along that path, we know that the function will increase without bound. And then if we choose the path y equals x and evaluate that limit as x approaches infinity, so with every instance of y, I'm going to replace it with an x, we would get 4x squared minus 8x squared plus x squared, which is negative 3x squared. This would become a 3y. The 3y would become a 3x, excuse me, and then plus 5. The limit of this expression as x goes to infinity is negative infinity. So traveling along another path as x approaches infinity, we see the function goes to negative infinity. So there is neither a global maximum nor a global minimum for this particular function. And I want to show you what this looks like. So you bring this over, and let's see if I can spin this around a little. This is the graph of the function 4x squared minus 8xy plus y squared plus 3y plus 5. And right there, I've got it marked with a black dot. That's the point 1/2, 1/2, 23/4, and you can see that it is behaving as a saddle point. So the horizontal tangent plane would exist there, but it's neither a maximum nor a minimum. And you can also see this appears to be going down forever, and it would continue upwards if I were to let the bounds go even further. Okay, so let's look at one more example. The function g of xy equals 1 over x squared plus y squared. I want to describe the behavior of g. Once again, we'll find all the necessary derivatives. This time, I would argue that there are many more algebraic steps in arriving at these particular derivatives. These are the first partial derivatives, and these are the second partial derivatives. again, I would encourage you to perhaps pause the video and make sure that you can achieve this partial derivative with respect to x, this with respect to y, and then all the second partial derivatives as well. There would be some necessary factoring out of expressions raised to negative exponents. You're using the quotient rule extensively in finding these derivatives, but as a student of Calculus 3, you should be able to produce these. So make sure that you can do that. Now, the gradient, remember, would be the vector valued function where this is the first component and this is the second component. And so we would be looking at, to find critical points, where is the gradient equal to the 0 vector? So this would be, under what conditions would the gradient produce the 0 vector? Those would be critical points, as well as under what conditions is the gradient undefined? Those would also be critical points. So the only way for the gradient to equal 0 would be if the numerators were 0, right? A fraction is equal to 0 if the numerator is equal to 0, as long as the denominator is not also equal to 0 in that case. Right, so we can get 0, 0 if we make x be 0 and y be 0, and that's the only way. But there's even a problem with that. If we make x and y both be 0 in order to get the numerator 0, it also, at the same time, makes the denominators equal to 0, and therefore the point 0, 0 is not even in the domain of this function if you go back and look at it. So 0, 0 is a place where the gradient is undefined. It is a critical point, but that point is actually not in the domain of the function. And since that is the only critical point, G has no stationary points, and therefore no local extrema or saddle points. And if we try to examine the end behavior again, we can look at a couple of different limits here. As the limit as x approaches 0 of g of x 0. So I'm looking at the path y equals 0. If I go back to this expression and replace every instance of y with a 0, I'd get 1 over x squared. And if I look at the limit as x approaches 0 of 1 over x squared, we see that that goes to infinity. So there appears to be no global maximum. And then if I look at the limit as x approaches infinity along this same path y equals 0, so I'm still in the same path, I get that the limit is 0. So as x increases without bound, the function gets closer and closer to 0. As x approaches 0, the function gets closer and closer to infinity. So collectively, these two items mean that there is no global maximum and that the function is itself always greater than 0, so in a way it asymptotically approaches 0, and so it also has no global minimum. So now I'd like to show you a picture of the graph of this function. Okay, here we go. So this is 1 over x squared plus y squared. So you can see that's the bottom of it. Notice it's flattening out into this plane. It's on the xy plane. So it never actually gets to 0, and then as you get close to 0 and from either x or y or any direction, it increases without bound. It does not stop at 15. It would continue. It just can't resolve that on this graphical program that I'm using right here. So no global maximum, no global minimum, and no stationary points, no extreme values, none of those. It's a pretty boring function, I suppose, with regards to the second derivative test. And that's all the time I have for this video.